Alright, so we are back doing hacker rank problems, the Project Euler ones. I'm skipping number 2 just because it had a very high success rate. I think the first one had a 50% success rate and this one has a 60-something. So we'll just skip on to this. Again, I'm going to be using Python just for readability and ease of explanation. If you guys want to see any different languages, feel free to let me know. So here we want to find the largest prime factor. So essentially we're going to be given some large number and we need to find its biggest prime factor. So here they give us the input that we're going to get is t and n, number of trials, and the number that we're using. Here we have 2 trials, 10, its prime factors are 5 and 2, the largest of which is 5. 17 itself is a prime, so therefore its largest prime factor is simply 17. So again, just to reiterate, we're given a number n, we just want to find its largest prime factor. So we're given this template. Again, t is going to be our number of trials, a is going to iterate over the number of trials, and n is going to be the number that we are investigating. So we could simply start, again, whenever you start these, just think the absolute dumbest thing you could possibly try, do that. So first, we know no matter what we do, we're working with primes. So let's go ahead and define a primality check for some number p. And what we're going to do is, again, just the dumbest thing, we'll optimize this a little bit. So for I in range p, we check if I mod, or if p mod I is equal to 0, that means that I divides p, and it means that p is not prime, so we return false. If we check every number and no number divides p, then p is a prime, so we return true. And what we want to do is start at 2 here, because 1 will always give us vacuous true, and which does not indicate that whether or not p is a prime. And again, we can optimize this. I know maybe some of you see this and think, wow, that's the worst primality test I've ever seen. I assure you, we'll optimize it if we have to. I just want to see if HackerRank will let us absolutely brute force some of these problems, which in the first one, it didn't let us, and it led to kind of a semi-interesting solution. So we'll see if this is the case as well. So we iterate, again, over factors. So for I in range 2 to n, and we actually want to include n because n could be prime, so we're going to check all the possible factors of n, and we're going to say if n mod I is 0, it means that I is a factor of n, and prime q I is prime. Then what we want to do is first store a max prime, and let's just say that this equals 0, and then we'll simply set max prime equal to I. And then once we're done, we will print max prime. So let's go ahead, run this, see if it gives us a correct answer. So we're getting correct answer so far. Let's go ahead and submit the code, see if we get timed out on anything. And as was the case before, we have 2 cases that are spitting. These will probably be timeouts, but we will see. And there we go. Timeout, timeout. All right, so we're getting correct answers. We're just getting timed out. So let's optimize this. The first thing I want to look at is the primality test. So let's think of maybe some ways that we could optimize this. The first thing that I would want to look at is to notice, and let's just use something like 16. So 16 has factors 1 times 16, it has 2 times 8, and it has 4 times 4. And we also know that the square root of 16 is 4. Now, a key insight for this is to notice that one of the factors, 416, is less or equal to the square root every time. 1 is less or equal to the square root of 16. 2 is less or equal to the square root of 16. 4 is less or equal to the square root of 16. So And this has to be true for any number, because you could imagine if you had two factors that when multiplied together equaled the number and they both were greater than the square root of the number, it makes no sense because square root of n times square root of n should be n. So what we're realizing here is that in order to check if something is a factor, we actually only need to ever check up to the square root of the number, because if it had a factor, we would find it before we actually reach the square root. Because the worst case scenario that could happen is something like 9, where 9 is 3 times 3, and we have to check all the way up to the square root. So rather than doing this, what we're going to say is we'll start by having I equal 2, and then we'll say while I squared is less than p, actually we should do less or equal, and this is the same as just while square root I is less or equal to p. We will go ahead and check if p mod I equals 0, then we have found a factor of p, and we're done. We simply return false because it is not true, and if we make it through everything, then we can return true. Now, another insight that we're looking at is maybe, once we test if 2 doesn't divide p, then certainly no other even number could possibly divide p. So why not just start with something where if I mod 2 is, if p mod 2 equals 0, then we return false. The only problem with this is that we now have to check if p is actually 2, and in that case we return true because 2 is a prime. Now the reason that what this allows us to do is rather than incrementing I plus equals 1, we can now start at I equals 3 because we've already checked 2, and now we only check the even numbers. So simply by checking only up to the square root, we've reduced the amount of computation by an exponential amount, and by checking only the odd numbers, we have now reduced it by half. So this primality test itself is already much faster, but we can do better. Now, one thing that you'll notice is that max prime here, it's always increasing. So it doesn't actually make a whole lot of sense to start from the lowest potential factor, and go all the way up. So really what we would want to do is, instead of this, we would want to start at n, decrement all the way down to 2, which again, Python loops are exclusive. So by ending at 1, we're actually ending at 2. And we're going to decrease by 1 each time. And then what we'll say is the same thing is if n mod I is 0, I is a factor. And if I is prime, then we know that it's a prime factor. So what we'll do is simply print I, and we'll go ahead and break out of this for loop because we found the maximum factor. There's no reason to continue investigating potential prime factors when we've already found the largest one. So we can go ahead and get rid of this one. But again, maybe you're thinking to yourself, why would I only decrement by 1? There must be a better way, right? If I'm looking at something like, actually let's use a different number. Let's use 24, right? And there's a whole bunch of numbers that could be factors all the way up to 24 itself. So we first check 24 and we say, are you a factor? Yes, you are. And are you prime? No, you're not. So we would need to go on. And what you'll notice is that we would check 23. There's no way that that could be a factor. You'll check 22. There's no way that that could be a factor. 21, 20, so on and so forth. And in fact, we won't hit a factor until 12. And that, again, has to do with these multiples here, is that the multiples are going to be in the form of 1 times some number, 2 times some number. We don't get 3 here, but then 4 times some number. So rather than simply decrementing by 1, what we could actually do is just check n divided by I for I in range, and again, we could just do this all the way up to n. It doesn't matter because this for loop is going to terminate early now for each time. So rather than looking at the number I, we're now going to look, oh, and I should actually start this at 1, and it should go up to n plus 1. So rather than looking at the number I, we're going to look at n integer divide by I. And the first thing that we want to do is if n mod I equals 0, then we know that n divided by I is an integer. So then n divided by I is an integer. And you could keep in mind that this number is going to start out really big, right? Because first I is going to be 1, we'd be checking 24. Then it will be 2, so then we'd be checking 12. And then it's going to be 3, so then we'll be checking 8, and so on and so forth. So this is an integer, as we said, is integer. So then what we want to do, and we also know that n over I is a factor, and n over I is a factor of n. That's really the most important part. So then we could simply go ahead and check to see if n over I is prime. So if prime q n integer divided by I, then we know, because again, these are decreasing factors and they're going to be exhaustive. It means that we're starting with the largest factor. Then we could simply print n integer divided by I, and we go ahead and break out of the for loop, and that will find us the largest prime factor. And now let's run it for a sanity check, make sure there aren't any bugs. So we have a, yes, I should be equal to 3. That was, I believe, originally part of a for loop. So we're getting the correct answer. Now let's see if we, and we're already no longer getting timed out. Very, very quick. So we've managed to speed that up by actually a tremendous amount. So again, if you guys have any questions about the solution here, feel free to ask. I'll try to answer them. If you have any criticism or feedback about the video, the format, whatever, feel free to mention that as well. I'm not opposed to changing things or making it more enjoyable for people. I hope this is helpful, and again, feel free to ask questions.